Welcome everyone to the TransferLab seminar, which is part of the Applied AI Institute of Europe. Our seminar is a platform where researchers and engineers share and discuss recent advances in AI and machine learning. In today's seminar, we have Pawan Goyal, who will talk about generalized stability-guaranteed quadratic embeddings for nonlinear dynamical systems. And Pawan is a senior AI engineer at the Applied AI Initiative, and before that, he was a team leader at Max Planck for dynamical systems in Magdeburg. So with that, welcome Pawan. Thank you for being here, and the stage is yours.
Thank you, Ian, for a very nice introduction, and thank you for also giving me the opportunity to present some of the work which I have done while I was at Max Planck Institute. So it has been a while since I gave this kind of talk, but I think I'm very happy to present some of the work which might be also relevant to many people who are working towards learning dynamical system from data. So today in this talk, as I said, most of the work is done while I was at Max Planck Institute, and this is a joint work with Peter Banner, who was my supervisor, and my colleague Igor Pontestov. And today's topic is said learning dynamical system, but particularly I will be focused on what I mean by quadratic embeddings, what notion of stability we are using to improve the learning aspect of dynamical systems. Okay, so typically what we of course see dynamical system almost every day in our life, and they are very, very important aspect if you want to do engineering design studies or any control design studies. So dynamical system plays a very important role if you want to study how the system will behave under certain operating condition. We want to go to point A to point B maybe in optimal ways, or some cost minimization aspect of it, or there are some design parameters which we want to optimize, or we want to see the how the prediction would look like. So to answer all of these questions, we need a dynamical system which can help us to answer some of these questions. So that is the setup, actually, the dynamical systems and then their applications. So in that context, what we would like to have a dynamical model or mathematical model which can describe our dynamics of the process. And in very, very simple words, what we are interested into learning a continuous dynamical systems where you have x dot is equals to f of x. This can describe basically, let's say, any dynamical system in a continuous setting. We have seen a lot of approaches in the recent time in the neural network settings, recurrent neural networks or neural ODEs, LSTM. These all are the kind of neural network which can help us to describe the time series or dynamic processes. However, the more information we have from the process, and we know a lot of information coming from physics, for example, some empirical knowledge, and if we can leverage this knowledge, we can make the whole learning aspect of it much more efficient. The problem setup which we have is a construction of mathematical model which actually can describe the dynamics of the process, and typically we are interested in this talk is a continuous dynamical systems. That means that we are interested into this mathematical function x dot is equals to f of x. As said, there are a lot of approaches which are being built in the neural network setting, LSTM, RNN, and then neural ODE, which is picking up to learn the dynamical systems. But the more information we have about the process, so if we are working, for example, chemical plants, then we know a lot of things about the chemical plants, for example, and then we would like to make use of this information which we have in the learning process so that we can either work with the limited data or we can make the learning whole process in much more robust. So there are, like I said, there are many information sources. We can be physical laws, or there are some domain knowledge. People are working and have observed a lot of empirical experiments. For example, they have done it and they have obtained a lot of knowledge, or we collect the data and try to learn from the data. Typically, we would like to use dynamical system to perform the engineering studies, and the parameter optimization control is something which we want to do it. And classically, we would like to have this model also as simple as possible so that we can do this whole design study in much more efficient ways. When it comes to simple models and dynamical systems, the simplest model which we can think about linear system, because the life is so beautiful in linear systems, because there are many times analytical solution if you want to do optimal control, or you want to feedback control, or optimization, there is an analytical solution also if you want to make a prediction in the linear settings. This is the, let's say, one of the ideal world which we can live in, so linear dynamical systems. And if you want to build a linear dynamical system from the data, and assuming that we have the derivative information for now, and then we have collection of data, then we can set up an optimization problem, which is x dot is minus ax, and then we can just learn the linear operator, and we can build a linear dynamical systems. And this is also referred now much more in the DMD, dynamic mode decomposition, or nowadays people also call it in the frame of operators and the linear operator learning or operator inference settings. So once we learn the linear dynamical systems, and if you happen to be in situations where linear systems are good, and then we have verified in experiment that linear models are working in your experiments, or your behavior is almost linear, then we can deploy and perform engineering design studies based on it. However, the world is not super nice, and there might be a lot of measurements which we cannot measure it. So that means we have partial measurements, or the world is full of non-linearities. And that means that if you want to learn a linear models, then we can only observe a very local behavior, and we cannot capture the global behavior or global dynamics with the linear dynamical systems. And therefore, we need to go somewhere into nonlinear settings. So as I said, the world linear dynamical system may not be enough to capture the complex dynamical behavior, but still we would like to have something like linearities. And for this one, then there is a lot of work which is going on nowadays is a Koopman operator and dynamic mode decomposition. And I would like to give a glimpse about the Koopman operators and what it is in a nutshell. So typically, if you have any nonlinear dynamical systems, let's say x dot is equal to f of x, what the Koopman operator says is that we can write this nonlinear dynamical system as a linear dynamical system, but typically in the infinite dimensional Hilbert space. So there exists a mapping from the X to some other space, and typically can be infinite dimensional, but in that space, the dynamics will evolve linearly. So that is actually very, very nice things, and that is actually coming from the very almost like a century back from the Koopman in the 1931, where he really proved all the theorems that says that any nonlinear dynamical systems can be written as a linear dynamical system exactly, but infinite dimensional Hilbert space. But as we know that typically for the computers, typically may not be good to work in the infinite dimensional. We need to have a finite dimensional approximation of it. And there is a lot of work going on nowadays into how to approximate this infinite dimensional Koopman operator to a finite dimensional so that we can do all the computations very efficiently. And that is actually leads to the notion of extended DMD. That means that we try to make some observables which actually will try to approximate this infinite dimensional operator as a finite dimensional linear operators. So typically for that one, actually, if you want to approximate this infinite dimensional linear operator by the finite dimensional ones, then we need to have some kind of a notion of observables. And then typically we do with the hand designs that we can make, for example, a dictionary which has all the polynomials, for example, or any other basis functions. And then we try to map using this basis function which can be approximating these infinite dimensional Koopman operators. So maybe there's a bit of a theory here, but I will give you some examples that how the things can be done so that maybe we can understand it. So let's consider this is a nonlinear dynamical systems, which is a quadratic. So you can see it here is the derivative of x2 is x2 minus x1. So this is a quadratic nonlinearities. But if you try to introduce a new variable, which is x2 is equals to x1 square, and try to write differential equation for variable x3, and we do all the computation, what we'll see is like now try to write a dynamical system with the three variables, x1, x2, x3. What we'll see is a linear dynamical systems now. So we started with the quadratic nonlinear dynamical systems, but we can lift this nonlinear quadratic dynamical systems as a linear ones if we introduce a new variables. And that is what actually can happen is sometimes we can finite dimensional linear operator, but generally it is not the case. But it can happen that sometimes we get it, but sometimes it can happen even for simple example like pendulum, which is we know looks like simple, but there exists no finite dimensional approximation which can exactly represent the pendulum dynamics in the finite dimensional as a linear systems. However, we can approximate it by truncating some of the higher frequencies, but it will not be an exact representation in the finite dimensional linear settings. And the reason is typically what we have is a continuum of spectrum. So the pendulum has an infinite eigenvalues, which is actually continuous. And that actually leads to that case that we cannot do finite dimensional approximation. We actually always have to have infinite dimensional if you want to have an exact approximation of pendulum as a global linearized representation of these dynamics. So these are settings. In some cases, for simple cases, it might work out that we can find a very good approximation or very good representation of nonlinear dynamical system as a linear ones, especially if the original system has a finite eigenvalues of it does not have actually continuum spectrums. However, in the world, there are many other examples, like even simple pendulum, where it has a continuous spectrum, and that means that we cannot approximate the nonlinear dynamics of pendulum as a linear dynamical systems in the finite dimensional setup. So that was actually the world from the Koopman things. As you see, there's in some cases, we can make a finite dimensional approximation, or we can lift systems as a linear ones, but many cases not at least like exactly. But however, our goal is still remain the same, that how we can find a common structure for all the nonlinear systems, or at least the smooth nonlinear systems, which can be exactly represent in the finite dimensional, and I don't have to deal with the infinite dimensional ones. But in the Koopman theory perspective, the structure is linear structure, but I think the downside is that we might have to deal with the infinite dimensional systems. And that means either they are very high dimensional or they are not possible to approximate in the finite dimensional. This leads to we are still interested into having a common structure for all the nonlinear system, but in the finite dimensional ones. And this leads to us to think about in the direction of lifting principles. That means that we want to go a little bit defining a new observables, but a little bit different setting. The setup which we are going to discuss today is in the presentation is kind of goes back to much more in the optimization world. And this is actually the McCormick who come up with how we can relax nonlinear convex optimization problem by the convex one, but in the higher dimensional one. So typically in the optimization is kind of very well known that if you have a complex optimization problem, then we try to lift the optimization problem in the higher dimensional. Probably in the higher dimensional problem is much easier to solve and maybe still convex, and it allows us to solve all the problems dimension increases, but it is much more efficient to solve that problem. This kind of principle, we would like to also use it, and the similar ideas has developed a lot in the dynamical system, and Koopman was one of them. But I think we're going to discuss in this direction differently, and that how we can go from the linear to other nonlinear system, which has a common structure, is still simple, but we can have, or we can work with the finite dimensional systems. And this leads to quadratic dynamical systems, and it has been shown that every nonlinear dynamical system, if it is smooth, assuming that your system is smooth, then there exists a finite dimensional lifting or finite dimensional mapping from the y to another variable with the y, so x to y. But this mapping is a finite dimensional mapping, and the dynamics of the y can be given by quadratic systems. So what it says is that we can go from x to y in the finite dimensional, and y is also finite dimensional, but the dynamics of the y I can write as a quadratic systems. And I can also come back from the y to x back. So all the dynamics actually will transit only as a quadratically in the different space, which is actually in the y. This kind of principle has been developed initially in the 1987, I think, which you can track in the perspective of control systems, or we want to design a control system for nonlinear dynamical systems. And this is given by the Soagu and Voigt in 1987 phase, which they use this principle of rewriting nonlinear systems as a quadratic systems, because then at least the controlling quadratic system is much more easier than a general nonlinear systems. Similar ideas or similar principle has been used in the reduced order model communities to compute or to obtain a compact model for nonlinear dynamical system as a quadratic dynamical systems. So let's look at the simple pendulum example. Actually, as we said, it is not possible to write as a linear system. However, if you have this pendulum equations, and let's say that we can introduce two more variables. So we are going from the x1 and x2 to we define two more variables, which is sine of x2 or cosine of x2. And this is, let's call them y3 and y4. So in total, we have y1, y2, y3, y4. And then we can also go back from the y to x, basically that mapping, we know it. And if we try to write dynamical systems for the y variables, what we will see is actually quadratic dynamical systems. If we try to write a differential equation for the variable y, we will see it is actually a quadratic nonlinearities. If you want to do approximation as a linear dynamical system, it's not possible, but we can do for nonlinear dynamical systems, including the pendulum, which has a continuous spectrum, basically. So which was not possible for us to do with the linear system. But if we go a little bit away from the linear to quadratic systems, then we can also do the things which we, or the continuous spectrum dynamical systems. Cool. And there are a lot of theory has been developed, how many variables we need it, can we upper bound it, and what is the optimal lifting, and if you know the dynamical system, what will be the optimal lifting. So there are a lot of work going on that how we can write a nonlinear dynamical system as a quadratic dynamic systems if you know original differential equation, for example. Typically, just to recap a little bit pictorially, so what we are interested into writing a nonlinear systems as a quadratic dynamical systems, and the beauty of this approximation or this lifting is that it is always in the finite dimension. It has been shown that every smooth nonlinear systems can be written as a quadratic dynamical systems in the appropriate space, or that it means that we have to introduce some more observables, or we have to lift the n-dimensional to higher dimensional dynamical system, but the dynamical systems becomes much more easy in some sense. So we are going from the original space to like a G space, and the dynamics or basically G can be given by a quadratic dynamical systems. What we can see is like we can do the lifting, which we can nowadays we can think about the encoding, but it's not encoding going down, but encoding in the high dimension. So actually the space can increase it, and then we can actually go back from the high dimension to low dimensional to the space where we are interested in. As I said before, if you know the dynamical systems like a two-dimensional pendulum, I could rewrite maybe with the hands, like what will be the observables or lifted coordinate systems, where I can rewrite my original dynamic, nonlinear dynamical system as a quadratic dynamical systems. But if we are in the data-driven setting, then we actually do not know a priori our dynamical systems, like we don't have the differential equation at hand. So therefore, that means we would like to learn everything from the data. So that means that maybe we can define a problem. What we have is like given the data, so X at the different time snapshots. And for now, let's assume that derivative information is given. So then what we are trying to identify in observables, G, which is actually, as we have seen, that there always exists a finite dimensional G. That means that I can go from X to G. But however, I would like to go in a very specific way to G, in the sense that the dynamics of the G can be given by quadratic dynamical systems. And then I can come back from the G to the X. So this is actually the problem statement. Now we can formulate it. And since we do not know any of these variables, so we don't know the mapping, we don't know the operator A and the Hessian H and B. So what we can put it in everything in optimization sense, basically. So we could try to learn it. And for that setting, basically what we can do is like classify the loss function. Loss functions are very classical ones for now. So the first is like autoencoders. That means that we want to go to X to the G, and then I should come back from the G to X. So that means there's a classical autoencoder loss, the first one. And the second thing is like we can actually, if you know the derivative information, I can also compute the derivative basically for the X dot. So it's like typical algebra there. There's nothing fancy here. So we can compute the derivative of X, and similarly, we can also compute the derivative of the G, which is actually some mathematical formula, but it's just nothing but the chain rules. And we try to also look at how the derivative information is also passed, and so that we can constrain the dynamics for the G as a quadratic systems. As I said, that maybe to train these things, there are different components now, basically like two neural networks, which you can think of. And there's like one is encoding and another one is decoding. And then we have all the matrices which actually define the dynamics of this latent space, which are matrix A, H, and B, basically. So, and then we can combine all the components, maybe with the different weighting systems, which you will like typically we have used only like same weighting, lambda 1, lambda 2, lambda 3 are the same, but we can also give like different weighting systems. So these are typically, let's say, the training loss, and then we can just do the gradient descent. Maybe the things will be nice, but things do not work. The thing is that when we try to integrate the latent space, then the latent space cannot be integrated, or we cannot make the prediction correctly. So typically you will get like unstable systems. And typically what we have is a continuous dynamical systems, but in the formulation in the loss function, we have not used any property of dynamical systems at all. So we just have a data, and then we just try to fit a classical autoencoders and some loss functions for the derivative approximation. But as such, we have not used any property of dynamical systems yet. In this talk, the property which we are particularly interested in is the stability properties of these dynamical systems, or we can think about the stability property of the dynamics of the latent space we are interested in. We started looking into some of the stability concepts, and I will start with a very, very simple stability concept from the linear systems. We have a linear dynamical systems, x dot is equals to a of x, and this system is asymptotically stable if and only if all the eigenvalues lies strictly in the left half plane. So, and that means that if the system will be asymptotically stable, that means that the x of t at infinity will go to 0. So this is actually stability property of linear dynamical systems. So then if you want to impose this dynamical system or the constraint of stability in learning linear dynamical system, for example, so what we can have, initially we had like an x dot minus a of x. If you want to learn a linear operator, that is fine. But if you want to learn a stable linear operator, which happens a lot in the control theory, that our system is, let's say, at least asymptotically stable, that means that we want to enforce that all the eigenvalues of A lies strictly in the negative half plane. And this problem is non-smooth optimization problems and can be very expensive, and also that it is really not easy to put in the formulation which we have seen before, that we want to learn the latent space and then we want to, let's say, put some kind of a constraints in the dynamics of the latent space. And these constraints could be not only like learning quadratic dynamical system, but we would like to learn a stable quadratic dynamical systems. Putting a constraints on the linear matrix, or in terms of that all the eigenvalues should lie in the negative half plane, it is, as I said, it is a non-smooth optimization problem and it's not so easy to solve it. However, there are some parameterization which we can think of, which will characterize the stable matrices. And this leads to some of the work which Gilles and Sharma has done in 2017. So we can take any stable matrix, A matrix, which has all the eigenvalues strictly in the negative half plane, can be parameterized as J minus R times of Q, where the J is a skew symmetric matrix and R is an R and Q are SPD matrix, like symmetry positive definite matrices. And that means that if we can parameterize our matrices J minus R times Q, that matrix by construction will be stable matrix. The parameterization allows us to not to look into non-smooth optimization problem, but we can fuse this parameterization directly in the learning dynamical systems. That means instead of learning only A matrix, what we have in different optimization problems now, we have like an x dot minus J minus R times Q times of X, but now we impose some of the constraint on these matrices. So if we can solve such an optimization problems, then by guaranteeing what the linear operator which will construct as a J minus R times of Q will be a stable operator. Since these constraints are not so easy, so we can actually also further relax it. That means every skew symmetric matrix can be parameterized like J minus J transpose, and relaxing somewhat. So instead of SPD, strictly SPD matrices, we can actually do like kind of either Cholesky factorization or the low rank Cholesky factorization, which we can think of. So we have the R tilde transpose and the Q tilde transpose to obtain the Q matrices. So we further relax it, and now we do not have any constraints or like an skew symmetric or SPD, but now we have regular matrices J tilde, R tilde, and the Q tilde, and we would like to solve such an optimization problems. And once we solve it, then we can construct our operator, linear operator, which will be by design will be a stable operator. And now the beauty, which is not there anymore, that we have analytical solution, because initially we had just an analytical solution if you want to learn a linear operator, but now the problem becomes much more involved, but it comes with a stability guaranteed. But however, nowadays there are a lot of fancy optimization algorithms based on the gradient descent. Probably we can write a gradient descent on top of it, and then we can optimize for these matrices. We can move a little bit on the quadratic system. This actually was our interest because we have learned the dynamics of this latent space, like a G, to be a quadratic system. So we would like to see that how we can extend this notion of linear stability to quadratic stabilities. If you want to use only local stability for quadratic systems, that means that if you want to, in that case, we only have to look at the linear operator, which actually defines the local stability, local asymptotic stability. That is kind of quite easy to do it. And then once we only would like to learn a local stability, then we just have to impose the constraints on the eigenvalues on the A's. And then now we know already how to parameterize this matrix like A, which is stable. And then we can actually fuse the linear matrix, which are stable. And then we can use this parameterization in this one. And then we can have basically local stabilities. However, if you have a highly nonlinear systems, and if you only look at the local stability, then it's not actually enough for us in many practical examples or practical cases. And therefore, we are interested more into global asymptotic stability of quadratic systems. If you are looking into global asymptotic stability of quadratic systems, and it goes back to like half a century ago when the Lorentz was working on this kind of similar stuff, and then he introduced a concept of energy preserving quadratic nonlinearities. And what does it mean is that if we have a quadratic nonlinearity, which let's say h, x canonical x, and it says to be energy preserving, if you multiply this nonlinearity by the x transpose, this will give you actually 0. And that means that energy is somehow stays in the system and doesn't lose the energy, or nor it generate the energies, more or less. And this kind of nonlinearity actually happens a lot in a lot of flow problems, for example, which you can in Navier-Stokes. If you have, for example, particular boundary conditions, like periodic boundary condition, then it happens to be the case that we have energy preserving nonlinearities in the Navier-Stokes. And this is actually where this all came, and it was picked up by the group of Nowak in the 2015, and there has been a series of work in this directions. But this energy preserving quadratic nonlinearity x transpose h, x canonical x to be 0 is not super, like we cannot use in the optimization sense, but how we can actually put these things in the optimization sense. But let's say that we can construct some matrix H, which will satisfy this condition, x transpose H, x canonical x is 0. And if we have this kind of dynamical systems where the age is stable and H follows this principle, then the overall quadratic system will be globally asymptotically stable. And we can also write the Lyapunov function for this ones, and we can see that this is actually a Lyapunov function for this quadratic systems. But how to parameterize this kind of energy preserving matrices so that we can use in optimization sense, because typically we don't know how to parameterize this kind of nonlinearity if energy preserving x transpose h, x canonical x is equals to 0. But if we can parameterize your H matrix, which is actually, you can think of Hessian, then you can think about this H is being consist of several skew symmetric matrices. So they are like matrices H1 to Hn, where the each of Hi or H1 to Hn, they are skew symmetric matrices. And if these are skew symmetric matrices, then we can easily see it that it will follow these properties. And what we have proved in this paper is that this condition is if and only if. So every matrix which is this form can be written in this skew symmetric form. So it's not a special case, but it's an if and only if condition here. So this goes both ways. So these are some of the concepts which we have utilized it to have a global stability for quadratic systems. So in that sense, how our loss function changes. So our first loss function is actually encoder decoder things. But now what we have is when we look at the derivative loss for the x dot, then we have the matrices A and H and B, but now all these matrices are constraint matrices. That means it is coming from the A should be J minus R, and the H should be like skew symmetric or consist of skew symmetric matrices. If we put these things together, so then means that we not only learn a quadratic embeddings or latent space whose dynamics is quadratic, but it will be also stable by the constructions. Because typically enforcing stability is not super easy concept, but if we can find a parameterization which can be worked together with the quadratic optimization, then it becomes much more easier. Because then we do not have any hard constraints like subject to some like an eigenvalues perspective, but we actually fuse everything in the parameterization of the system. Then if we have this parameterization, then we can actually have like a classical loss function, and then we can actually train all these components together. So this is how we can actually enforce the stability of quadratic systems. So there are two concepts now that we would like to learn in embeddings or like latent space, which is quadratic. But on the top of it, we would like to learn a stable representation of the dynamical systems. And this will many times happen if your original system is either dissipative systems or energy preserving systems. So in that case, actually, we can use the parameters that we discussed just now. let's look at how it works. Basically, first example is a pendulum example, and maybe I'm just gonna quickly walk you through some of the results. So we collect we check like 50 random initial condition, some time interval 0 to 25, and then we choose also randomly position and the velocity for the pendulums. This is a 2-dimensional system. We lift to 3-dimensional systems and then try to learn a latent representation for these equations and also enforcing the stability. And we do the prediction not only for 25 seconds, but 75 seconds, so much ahead in the time. So this is what you can look, but maybe it's not super easy, but I will walk you through. There are some examples out of 100 testing cases. What you can see is we have compared with the 3 models, or maybe more details I can say we can refer to the papers. But I think the first red ones, what we have the linear embeddings, that means we try to approximate the systems as a linear dynamical systems. So what we can see is that it is not capturing the dynamics accurately. Black dot is the original one, so the ground truth, and this is actually the red one, the part which you see is from the linear dynamics. But if you relax this thing from the linear to quadratic ones, then actually we can actually nail it, and then we can capture for all the dynamics for the different initial conditions very well. If you don't use the autoencoders, we just try to learn a best fit quadratic models, then it also will fail it. So it actually shows the power of learning the latent representation, which are not linear, but the quadratic ones. Maybe this is a much more detailed graph for an absolute median error, but actually we also see in the quadratic embeddings, when we enforce the stabilities and then learn a quadratic systems instead of linear ones, we can do much better. Second example is also dissipative Lotka-Volterra, which also has a continuous spectrum. We also collect only 10 initial conditions, so not like large data set which we have it, and we also collect the data in 0 to 10 seconds. And we lift the systems into 3-dimensional systems, and we test what we learn for the 100 test initial conditions. And also the horizon is also much bigger in the test case than the training ones. So this is what you can see. So if you try to learn a linear embeddings, as you said, we cannot approximate in the finite dimensional here. So this is actually completely fails it. But if we relax this from the linear to quadratic ones, then actually we can capture all the dynamics very well. And if you also don't impose the stability, then also we will not get anything. So we have to impose the stability, which we have discussed, that on top of it to get something meaningful learning of dynamics in the limited data set. So here you can see that we only have the 10 different initial conditions. Same thing we also try to do in the high dimensional, so nonlinear Burgers examples for the PDE case. And for here, we actually replace the autoencoders with the convolution autoencoders, but the rest of the story remains the same. And now we learn 4-dimensional observables. So the original problem is 1,000 discrete points in the space. We try to learn the 4-dimensional latent representations, and this is what we can actually get very good learning of dynamical systems for the PDE case as well. Okay, this brings me to conclusions. And what we have discussed is the lifting principle for nonlinear dynamical systems. Basically, what we have discussed is that how we can write a nonlinear dynamical system as a quadratic dynamical system, but in the Liftrand space. And this lifting or this mapping from nonlinear dynamical system to quadratic one is exact, is not an approximation here. And that actually leads to the notion of quadratic embeddings. And the stability was actually a major factor to make all these things work together. Otherwise, we cannot work with the limited data and have a robustness. And if we don't impose the stability, that means we cannot integrate in the latent space very accurately. And that means that the overall dynamics is not learned properly. The thing which I did not discuss today is Hamiltonian systems, how we have extended this whole theory to the Hamiltonian systems, particularly canonical Hamiltonian systems. But I think maybe if somebody is interested, we can talk offline about it. But there are some work also we have done for Hamiltonian systems. A lot of work needs to be done. I mean, that is how to deal with unstable system, because sometimes it can happen that we have a system which is unstable, and if you impose the stable constraint, then it's not correct, basically. So it can happen if you have flow problems, like a flow past cylinders, then we have two unstable eigenvalues, how we deal with it. How to extend this whole framework for discrete system, parametric case, and control cases. We have done already some work for the control, but I think a lot of work for discrete system and parametric systems need to be done here. Okay, this leads to conclude my talk. Thank you very much for your attention, and there are some references related to this talk.